Hello everyone, we'll continue our discussion about quality of service. So in the last class we were discussing about what you would want from an application. What sort of performance would you want when developing a particular application? And it really depends on the application in mind. So we were talking about video streaming, and we said that if there is just a one-way transfer of data, let's say there was a cricket match and a server was transmitting data, what would the user want? How much of throughput and how much of latency would be tolerable, right? So the throughput is the amount of bits, you can say the amount of information that can be pushed across from one end to the other. And you would want a few megabits per second because that's the data rate you need for a video, right? Of course, if it's on a very small screen, then maybe you can get away with a little bit less than this. But if you want high definition, for example, you might need much more than 1 Mbps. Right? So depending on the requirements, you would have different throughputs that you would need. Also in terms of latency, so latency is the time taken for let's say a bit or a message to go from one end to the other. That's what we would call one-way latency. And we also talked about round trip time, which is the time for a message to go from one end to the other and a reply to be sent back from the other end, right? The time to go from one end to the other and back. So what would we want over here? So here in terms of one-way latency, it doesn't really matter. I mean, whether you see the cricket match a second later than when it actually happened or 2 seconds and so on, it probably doesn't matter, right? So latency that you could tolerate could be, I mean, it really doesn't matter, but let's say even a few seconds should be fine. That's, let's say, for a cricket match. But if it was just streaming, let's say a movie, a recorded movie, it doesn't matter. I mean, whether it takes 1 second or even a minute for the information to go from here to here, right? As long as there is a continuous stream of data coming through, that's fine. Okay. So even if a packet starts here at time t equal to 0 and reaches here at let's say t equal to 5 minutes for a recorded video, it doesn't really matter as long as after this you're seeing it continues, right? But of course somebody may be impatient, right? And he may not, when he clicks on the play, he doesn't want it to start 5 minutes later. Okay, so then maybe it should be much smaller. Right? So depending on what the user wants, I mean the quality of service would have to be given by the network. Right? What about file transfer? So you have, let's say, 1 GB of a file here and it has to be sent to the other end. What sort of throughput do you want? Right? So you might think to yourself, and really the more throughput you have, the better, right? So of course it's not so critical. If you have a 1 Mbps connection, it will take quite some time to get this. But if you have a 1 gigabit per second throughput, then this will download in a few seconds, right? And so the more you get, the better. But there is no critical throughput without which the application would not work. Right? And essentially the term for this sort of a QoS requirement is best effort. So best effort means an application will make do with whatever quality of service the network gives. The network will just do its best to send your information from one side to the other, okay? But there are no guarantees. So no QoS guarantees from the network. Okay. And it will transfer data as best as it can. So here the network is not giving you any guarantee. So suppose you want to transfer a file, for example, it doesn't tell you it's going to be at 1 Mbps or 1 Gbps or anything like that. Whatever the best the network gives, that's what it gives. There are no quality of service guarantees. And unfortunately for us, the internet was designed as a best effort network. So the internet, the current internet is designed as best effort. And a lot of work, of course, has been gone in, and a lot of research has been done to move away from best effort, to give better quality of service. So let's say that somebody wants a guaranteed throughput or some sort of a guaranteed latency, that it will be given, right? So lots of research effort has gone on from the 1990s and so on, a lot of effort on quality of service. But it turns out that it's very hard to change things in the internet. Okay, so I mean, if a particular router has been designed in a particular way with, to run a certain set of protocols, it's hard to go and change that router. Okay, and so it's been sort of difficult to get quality of service into the network. And we see that every day. You might do a Google Meet call or something else. Sometimes the quality is good, sometimes it's pathetic, and that's because of your best effort. So if there is a lot of capacity in the network available, you might have a high throughput, but otherwise not. And why does this happen? So let's think about it. If you go back to the router that I had described in a previous lecture. So let's say that these are various links. Let's say these are wires coming into the router, and we are focusing on one particular link. And I said that each of these links has a certain maximum bit rate, and the term to use there is bandwidth. So the bandwidth, and sometimes it's called link capacity. So these are terms used when we talk about wired links. So the terms bandwidth and so on have a little bit of a different connotation when you talk about wireless links. Okay, so it's just that different communities of researchers have done work in different fields, and they might reuse the same term in a slightly different fashion in their own research areas. You have to be very careful. Okay, so bandwidth here refers to the link capacity, which is the maximum data rate of transmission on a wired link. So let's say that this supports 10 Mbps. So this is a router which I am showing you in the internet, and we said that there are these packets which come in. Each packet has some application data but a lot of headers. We said each protocol layer adds its own header, right? So these packets have to be sent out on these links. The router might modify some of the headers, and send out the packet to the output link. So the router has to very quickly decide where are these packets destined to, right? And in the internet, at least at the IP layer, this is done in at least with a lot of hardware support, so that it's done quickly. Okay. So we said that the problem is that you have more incoming packets than you can push out on this link. You can only push out at 10 Mbps in this example. And what if all these links are 10 Mbps and multiple links get a stream of packets, a bunch of packets which have to go to the same output? They can't all be sent out immediately, so they have to be temporarily stored in the router itself. So you have a queue over here, an output queue. Okay. Which is there at this particular link. So the packets get put into the link and the queue empties it as fast as possible, right? The packets are sent out, it pushes them, but if there are lots of them coming in, they get over here. Now let's say that you were running a Google Meet application when your data was going through this router. Okay, so maybe your data is coming in on this link and going out over here. Right? This is your Google Meet data, and it's going to your friend somewhere at the other end of the internet. Now the question is, what sort of quality of service are you going to get? What is your throughput going to be? And suppose there was nobody else transmitting on the network, you could get as high as 10 megabit per second throughput. Right? So whatever you sent would go through very quickly, as long as you were sending less than 10 Mbps. Right? Because this link can support it. Of course, the situation is a little bit more complicated because there are routers all the way to the destination, and you'd have to consider all the routers along the path to figure out what sort of throughput you're going to get. But let's focus on this. Let's say that other links, are very high, gigabit per second or whatever. We don't have to worry about them. They're just this link, so we're getting 10 Mbps over here. And everything is fine. Your Google Meet, the video quality is crystal clear. You can hear the voice and so on. But now suppose other people start transmitting and they all are sending to the same link. Okay, so other people are sending 10 Mbps, somebody here is also sending, right? And all this data is going over here. Now you have competing connections just for the same link. So you are sending your Google Meet data along this link, and many others are also using the same link. So let's say that there were 10 or 9 other people and you're the 10th person competing for this. Intuitively you might get 1 Mbps. But of course, depending on the protocols used and so on, it might be different. You might get a little bit more or a little bit less than 1 Mbps. Right? So really the throughput that you get depends on what else is happening in the network. Who are the other people using it? Okay, so in the current internet, you can't reserve bandwidth along the different links. Okay, that's not a guarantee. That's not provided by the protocols. And in the original ARPANET which they were developing, they didn't need that sort of a guarantee, so they didn't build it in. So although people have done a lot of research and they've shown how to make such reservations and so on, and remember that if you want to reserve bandwidth on this link, that's not enough. You would have to reserve it on all the links from the source to the destination. So it's not trivial to do that, but it can be done, and there are lots of protocols to do that. But even if a Cisco router has that implemented, it may not be activated by the person operating that router for various reasons. I mean, because just that people don't use it, and to get all the networks across from source to destination to cooperate to do this sort of a reservation of bandwidth is non-trivial. Okay? So what the internet gives us is best effort. If you're lucky and nobody else is using the network, you get good quality, your throughput may be high and latency may be low. But if lots of other people are using the network, you may not get such good quality of service. Your throughput will decrease because other people are competing with you, and your latency also might go up. So why would latency go up? So let's just focus on this queue over here. This is the output of the queue. And we have packets coming in over here, which are getting stored, and normally they will be sent out in a first in, first out manner. So these packets are coming in over here, and let's say too many packets come in, so they might get stored over here in this particular buffer. So what is the time between when a packet enters a router and the time it leaves the router? Let's think about it. So let's say that this is a packet of size P bits, and let's say that this output link is C bits per second. So the question is, how much time does this packet have to wait in the router? Okay. So let's say that it's coming in on an input link. Let's say that this one had C1 bits per second input link, just to generalize it, and this output was C2 bits per second. So let's assume that the last bit has come into this particular link over here. Okay, so data is coming in at a particular rate, C1 bits per second, right? And so initially what is done at the input link itself, this is at the input, and this is the output link. Okay, your packet is coming. Think of it as being like a train car coming in, right? It's coming in over here towards the right. And interestingly, typically routers will not send a packet as soon as the first bit comes in into the output. Okay, and obviously you can't do that. When you get the first bit, how do you even know what the output link is? Right? You need a few bits to come in, at least to see the destination IP address, and then you can send it to the output link. Okay? But that's not done in practice. You wait till the full packet comes in, and only then. So let's say that this is a queue at the input link. And you put this full packet in over here, and only after the last bit of the packet comes in, you send it. And the reason that is done traditionally in networks is that you want to forward a packet and use resources at your output link only if the packet has come in uncorrupted. It's possible that there's a bit error or something like that, and if you start forwarding a packet as soon as it comes into the output, then you might be in trouble. You sent, let's say, 90% of the packet here, but then the last 10% is corrupted, and then there's a lot of confusion over here. You've utilized resources here and unnecessarily. Right? So you wait till the full packet has come in, you check it for any errors, and of course there are things like checksums put into the packet so that the router can figure out if there was an error or not. And if there is no error, it is put in the output queue, and that is called store and forward. So you wait till the full packet is received at the input, and then forward to the output queue. So this is the store and forward property of most of our routers today. There is another type of switching which is called cut-through switching. So here you don't wait for the full packet to come in before forwarding. Okay, so you forward to the output as soon as you can. Okay, so if you have to read the header to figure out where the output is, you would do that in cut-through switching. But let's say you want to do it based on the IP address. So as soon as the destination IP address is received, you figure out where it's going and you start sending the bits to the output immediately. Okay. Yeah, so that is another way to do it, but the risk is that you might waste a lot of resources in case the packet is corrupt. Anyway, so this is what is done. Let's say we are using store and forward. So it takes some time for the data to come in. So time, let's say the time at which the first bit was received is T0 here. Let's just write it all carefully. Let's say that T0 is time at which first bit of packet is received at input. Okay. So when is the entire packet going to be received? I think we'll use another page. So T0 is the first bit at input. Okay, so it's received at the router. And let's say T1 is when the last bit is received at the input. So T1 is equal to T0 plus packet size in bits, of course I'm writing it in bits, divided by C1, right? Because the link rate over there or the bandwidth is C1 bits per second. So now in store and forward, you wait till T1 before you shift the packet to the output. Okay. So let's say that the switching time is 0. So you have this router here, there is an input over here, we said C1 bits per second. And there is some sort of a crossbar over here, right? And packets are sent to the output over this crossbar. This is just a switching mechanism to send from various inputs to the output. Okay, and there are of course many output links. Okay, I'm just focusing on one of them. So the last bit of this packet of size P is received at T1 and that's when it goes to the output. So let's say that already the queue had some data, and let's say that the queue size at time T1, I'm going to call it QT1. Okay, so this is the size of the queue at time T1. Okay. So there are already some packets. I mean, it could be 0, that the queue was empty. Right? That would be good for us. But suppose it is QT1, then the question is, when does the first bit of this packet get sent on the output link? Okay, so let's say that T2 is the time at which the first bit is sent on the output link. So what is that going to be? T2 is T1, that's when the packet goes here to the output link, plus, okay, so let me just draw that. Let's say that I'm just putting the packet in this color. So the packet gets put over here. So this queue has to be emptied at, we said, C2 bits per second. So the queue has to be emptied, and this is divided by C2. Okay. And that's when the first bit gets sent out on this link. Okay. And let's call T3 is when the last bit of the packet is sent on the output link. Okay, I'm just writing output as O/P. Okay, I might write I/P for input, right? Just as a short form. So what would T3 be? It's going to be T2 plus packet size divided by C2. Okay. So which is equal to T1 plus the queue size when that full packet was received at the input by C2 plus P by C2. Okay, and if we want, we can even write it in terms of T0, right? So I just write that just for completeness, T0 plus P by C1 plus QT1 by C2 plus P by C2. Okay, so we wanted to calculate what is the latency of the packet, how much time does it have to wait at the router. Okay, so if we are looking at the time after the last bit comes in, how much time is required for it to wait. Okay, then of course that is this much. Okay, so this is called the queuing delay. And this is sometimes called the transmission delay. Okay, so because of this, why do we have to wait this time? I mean, if we didn't have store and forward, things could have been done much faster. We had cut through switching, right? But this is the time to actually take to transmit that packet out over here onto the network. Okay, so the time between the time from which the last bit reaches the input to the time that same last bit is sent out on this link is given by sum of these two terms. So latency is not zero, even if the queuing delay is zero everywhere at all the routers, right? Maybe you're talking at some point of the day when there's very little other traffic on the network. So this is another term used by networking people, traffic. So traffic is just all the packets going along the links in the network. It's something like you're thinking of it like a traffic in a road network, but instead of cars you have packets. So even if queuing delay is zero, you have these transmission delays, and your end-to-end latency, okay, from you to your friend who's at the other end of the Google Meet connection, is going to be the sum of these transmission delays. You're going to have the sum of packet size divided by these link rates, what I call bandwidth, right? But of course, if there is queuing delay, you have additional delays, right? And you have to sum them up across all the routers. So latency depends. I mean, there's no guarantee because we said it's really a free for all. It depends on what these queuing delays are. Sometimes the queuing delays may be high, sometimes they may be low. So in a best effort network, we end up with sum of transmission delays plus sum of queuing delays. So this is the queue size. In bits at time t. So we can also have packet losses, I said, because if this queue fills up, then the router doesn't know what to do with the packet. He will actually just throw away the packet. It will be discarded. Okay. So what we end up with in the current network is a best effort network where there's no guarantee for throughput or for latency. It really depends on the other traffic, and it's called cross traffic. So cross traffic is the traffic other than your own traffic. Other than one's own packets. Okay, so if the cross traffic is high, then you would have higher latency and lower throughput. But if the cross traffic is low, then the opposite would happen. Okay. So we all hope for low cross traffic, but it doesn't work out always. Right? So sometimes your Google Meet quality may be very, very poor. And you might think, why is it better if you actually make a regular telephone call? You don't do a Google Meet, you do a regular telephone call. Then usually the quality is not so bad. And the reason is that the telephone network was designed specifically for the voice application. So it actually guarantees some amount of bandwidth all the way from the sender to the receiver. It's only the last wireless link where you may have trouble, because there's a lot of interference and so on. We'll study that in the physical when we talk about physical layer. But otherwise, if you do landline to landline, the quality is pretty good. And even mostly when you do mobile phone to mobile phone, just a regular voice call, the call is fairly good. It's not as erratic as something like Google Meet or Skype or something. Okay, so how does this all work? And the protocols have to deal with it. There's one more thing which I wanted to talk about, which I hadn't mentioned in the last class, which is congestion control. So we said that at this output link, packets might start filling up the queues when the input rate is higher than the output rate. And if these queues build up, then we say that congestion has occurred. So queue build up at any router. So just like congestion in a road network, we have a traffic jam. And of course in a traffic jam, cars don't disappear, they are just stuck over there. But in the real network, you would just throw out packets, right? If the queue gets full, let's say this is the queue and it's full and another packet comes in, this packet is actually dropped. It's just discarded by the router. And we say that the packet is lost. Okay. So you can imagine if such a system persists, then really nothing is going to work. I mean, the quality of service of your application, the quality that it experiences is going to plummet like anything. Right? You'll just give up and stop using the internet. You'll just close your application. So we don't want that to happen. We want the network to still continue, and after all, we have intelligent protocols working over here, right? I mean, and why can't they cooperate in some way to take care of this congestion? And that is called congestion control. So in the original internet, congestion control was handled by TCP. So it's handled by transport protocol, by the transport layer, which is this TCP protocol handles it. Right? And of course you can replace TCP with some other protocol which does congestion control if you want, right? But it's just such a headache to get working correctly that you'd rather use the TCP implementation in your machine than trying to bypass it. Okay. So it's mainly handled by the transport layer, and what TCP does is it tries to infer if congestion is occurring. You can do that by looking at whether packets are dropped or whether you're experiencing higher and higher round trip times. And then you back off, you reduce the rate at which you're sending packets into the network. That's how TCP works. Okay. But there may be other layers too which do some amount of congestion control. Of course, it wouldn't be called congestion control, but if your link is being used heavily, there other protocols too at lower layers might try to do some sort of have some sort of a back off mechanism where they reduce their transmission rate. Okay, so it also may be handled by lower layers. So example, by the data link layer or the file layer and so on. Okay, so each layer is separate in some way. Of course, it has to be able to talk to the higher layer, the next layers above it, and the layers below, right? But it doesn't have to be able to talk to all the layers. But at the same time, what each layer does is not completely independent of the other. I mean, there's not a clear distinction between what each layer does. So I said TCP tries to handle congestion, but other layers might also try to handle it in some way, right? But they try to work more or less independent of each other. So you have the application layer. It has to be able to talk to and get data from the transport layer. And I am using the 5-layer model. If you look at the textbook, Peterson and Davey, and I've sent out the URL for the 6th edition they put out. Okay? It's nice of them to put the textbook, make it freely available to everyone. Okay, so they might talk about Osi 7 Layer, for example. So you would have, after transport, you have session and presentation layer and application layer, right? But nowadays, typically all those three are all pushed into the application software, right? So the WhatsApp will take care of how it presents the data to you, and the sessions, the various sessions with the server and so on. All of that is all bundled into the same application. And the operating system will provide the transport layer and so on, and parts of the lower layers will be implemented on the network interface card. Okay, so there we have the network layer. Data link layer and the file layer. So each of them performs different tasks for the most part, but there might be some overlap, okay, between what different layers are doing. So just to give you some examples, so in the current internet you would have FTP, HTTP, right? Different protocols working at the application layer. Okay, lots of acronyms, right? And we are familiar with them: file transfer protocol, hypertext, whatever, right? And SMTP is the protocol for mail, it's used by email, right? So the web uses this, email uses this, and a whole bunch of applications, right? You could think of, right? And below, what you normally get for free with any networking device, whether it's your mobile or desktop and so on, is TCP and UDP So TCP does everything you would want, taking care of reliable transmission, retransmissions of lost packets, congestion control and everything. And UDP does pretty much nothing, right? It's just a way, if you don't want TCP, you could go with UDP. And if you wanted to do congestion control at the application layer of your own type of congestion control, you would use UDP and do some sort of retransmissions of packet and congestion control in the application layer itself, right? So there are other applications, your voice over IP and so on, right, or your video conferencing applications, which might have built their own protocols, right? But all of these would normally use one of these, TCP or UDP, and there are other protocols which might use UDP. So voice over IP is your voice call using the internet, and it could choose to use TCP or UDP. Okay, but the problem with TCP is your packets might get delayed from one end to the other. If there's a packet loss, it might slow down. So in case you want your packets to get into the network immediately, you don't want them to be stuck at the transport layer, you use UDP. So UDP, as soon as it gets a packet from the application layer, will send it off to the lower layers. So here we would have IP. So IP is the glue, you can think, for the entire internet. It's a common protocol used everywhere, and it routes packets based on the IP addresses. Right? So this is the common addressing scheme for the entire internet. Below IP, what do we have? We have the data link layer, and there are various different protocols, right? So you might have heard of Wi-Fi, right? So your Wi-Fi is 802.11, that is the IEEE 802.11 protocol, okay, which handles DLL and the file layer. And on the same device you might have even an Ethernet connection, which is 802.3. Right, and IEEE is the standards organization which actually decides what these protocols are going to be. So you need to have standards because you have different vendors building this equipment. So they need to know exactly what is the data format and what exactly are the messages to be sent forth and so on, right? So the standards organization, right down to the last bit, they will say what has to be sent out, right? And there are various other things like your 4G LTE, right, and many other protocols. There are Zigbee and so on, right? So various other protocols, right, operating at the link layer and the physical layer. Right? And there are standards bodies which actually describe all of these in detail. So we end up with sort of like an hourglass figure for these protocols. It looks like an hourglass, right? So just the shape of it, right? Just because everybody is using IP, so you have a single protocol at the lower layers. So I said congestion control would be done at the transport layer, especially here. I just say that congestion control, but some of it might be done over here too. So I just say that some of it may be done over here. I just put a question mark there just so that you see what I mean later on in the course, right? Some amount of it could be done over here too in the Ethernet protocol. Right? And what about routing? So routing is handled mainly by the network layer, but some amount of routing is also done over here let's say at this layer, at the link layer. Okay, that's why we talk about L2 switches, because those devices, even though they don't look at IP headers, they do some amount of switching. They don't send the packet which comes on an input link to all outputs. They would send it to only a particular output, if they know where the destination is. Right? So, though these protocols, they are supposed to work more or less independently, and they are supposed to perform different functions, they might repeat some of the function a little bit, right? Yeah, but each protocol is designed so that it only has to talk to the higher layer and the immediate lower layer, right? So TCP has an interface to IP as well as to the application. Right? So when a packet comes in here into the network, suppose you are using Ethernet and a packet comes in. Okay, the link layers have to figure out whether the packet is meant for this device or not. If it's not meant for this device, it doesn't forward it up to the higher layers. But suppose it is for this device, it sends it up over here. And this higher layer has to figure out which of the applications it's meant for. Right? So there are some fields in the headers which indicate which application it is meant for. So there is a protocol field which tells you whether it's TCP or UDP or some other protocol which might have been implemented over here, right? And there is a port number. I'll just say port number, which tells you which application it is meant for. Okay, so each of these application should be using a different port number, and the operating system has to ensure that somebody doesn't reuse the port number for different applications. Right? So if you try to do that, the operating system will give you an error. It will say the port has already been used by another application. Okay, so we've tried to simplify a very complex task by dividing up the tasks into various protocols at different layers. Okay, and each layer tries to work independently of the others, but it has to be able to communicate at least with the next lower and next higher layer. In the current internet, a lot of the difficult tasks are handled by the lower layers. If you are building an application, you don't have to worry about retransmitting packets or congestion control or what format the bits have to be in, at the lower layers, and what signals to send out on the physical layer and so on. All of that is given to you. Okay, and if some protocol has to be replaced, it can be without affecting the other ones. Okay, you can replace TCP by, let's say, a new protocol which you build at the transport layer, or you can build a new application. Okay, so the current internet doesn't prohibit you from building a new application. And that's what made it so popular, that you can just build a new application and you're ready to go, with all these other features taken care of by lower layers. Okay, and you can also come up with a new physical or file layer for your own proprietary network. But if you want it to be widely used in the world, then it will have to go through a standards body. And the standards bodies are very difficult to, it takes a long time to get a standard through, because there are lots of companies jostling for their ideas to be pushed into the standards. So each company, usually before the technology is built itself, they come up with their own patented schemes. Right? Somebody might do retransmission in a certain way, or solve a particular problem in a certain way using a certain algorithm, and they patent that, and then they try to push that idea into the standards. Okay, so that's a typical game they play. So it takes some time for the standards to come out, but once it comes out, that's good for everybody, because then everybody can build equipment which is according to the standards, and then the different equipments from different vendors are interoperable. So I think that is enough for an introduction. And we will start looking at the physical layer in the next class. So sometimes people discuss networking from top down. Okay, so the QoS and ROS is a textbook which looks at the network. They start with the application layer and then go to the lower layers. But Peterson and Davey, which I am looking at, which we are using, there's a bottom-up approach. Right? So normally if you were building an application from start or a network from scratch, you would have a top-down approach. You would say, this is my application, this is the quality of service I want, and hence I want these protocols. Right? So you would go top-down. But unfortunately, right now we are stuck with the internet. So the protocols here are ossified. You can't change them easily from TCP downwards. So it makes sense now to go from a bottom-up approach. So you start from the lower layers and go up. Okay, because the lower layers, physical layer will just look at one link, and the higher layers will start looking at larger networks and so on. Right? So that's one way to look at it, and we'll follow this approach. Okay, so we'll start with the physical layer in the next class.